Good afternoon, everybody. So this talk is really an update on a 2-year project between these West Coast institutions and in close collaboration with both tsunami warning centers, with PTWC and NTWC, under the auspices of NASA and NOAA to infuse them with GPS data. So I'd like to start with a brief recap of why the tsunami warning centers exist. The tsunami warning centers exist because of this earthquake, the 1946 Aleutian Islands earthquake that had up to 13 meters of run-up in Hilo in Hawaii. And you can see in this model by Nathan Becker and Dailin Wang that the arrival time of the tsunami to Hawaii is roughly 4 to 5 hours. So when the tsunami warning centers opened up for business in 1949, this is kind of the time frame that they were conceptualizing their job to work in issuing warnings for these events in a matter of hours, and especially for full basin events like the Aleutian Islands event. And the way they work today is actually very successful if measured by that metric. They routinely issue warnings for large events worldwide, and they do it sufficiently fast as to alert people in Hawaii and Alaska that an earthquake has happened in Chile or Japan. And the way they work now is by relying on 3 measurement platforms. Really, the biggest one is the Global Seismic Network. Even though they're a tsunami warning center, they're really an earthquake center in many ways. And they use a number of algorithms. The details are unimportant here, but more or less the way they work is they use this thing called MWP that gives them a magnitude, regional and teleseismic magnitude in about 5 minutes. Saturates at about magnitude 8, but it's there in 5 minutes, and then W phase moment tensors, which many of you are familiar with, come in about 15 to 30 minutes. Then the dart buoys, which are very popular, are their second line of defense. The dart buoys are great. They directly measure the tsunami. They're not measuring the earthquake, they're measuring the tsunami. That's the thing that we care about. But they're spatially limited, they're expensive, there's only about 39 of them. And because they're in the abyssal plains far away from the trenches, it usually takes them more like an hour to 2 before enough data accumulates at a dart buoy or 2 or 3 dart buoys so that you can invert for the tsunami source. And then they have a third set of measurements is the global tide gauge network, which is surprisingly good. There's many, many tide gauges across the world, but they're really a detection of last resort, and they're used to upgrade or downgrade or change warnings as the tsunami arrives on shore. So what we're working on is to provide them with a 4th tool, real-time GPS, that kind of fits in nicely between all of these. We think that GPS allows them to have magnitudes even faster than MWP, but this is not meant to replace any of these 3 other tools. It's just another tool that they can use for situational awareness and to issue their warnings. So this really started almost 2 years ago to the day at a meeting we had in NTWC in Palmer in Alaska. And really the point of that meeting was to understand how the tsunami warning centers work, and for them to understand from us what wares are we peddling and what are we offering them. And what we came to understand, or what is to me the most important part of that meeting, is that seeing how they operate in real time. And what we learned is that quick response dominates, and by that I mean that they need reliable quick look products that they know have worked over and over and over again, so that when it pops up on a screen they can trust the number that's on there. And very importantly, the state of the art is hands-on. There is some automation, of course, but there's still a watchstander that makes decisions and pushes buttons to issue bulletins and warnings. And then we were there to figure out where GPS fit in, what kinds of data and modules would we build for them, and what the general architecture would be. So that was 2 years ago at Palmer, Alaska, and then we had a follow-up meeting last year in Honolulu at PTWC. So, but why? Why do we need GPS in the first place if the warning centers have been open for business for so long? The reason, I think, really was born as a result of the 2004 Sumatra earthquake. These are the numbers of casualties in several regions across that earthquake. Almost 250,000 people died in 2004. Almost all of them as a result of the tsunami, most of them in Indonesia, Thailand, and Sri Lanka. And what happened during that event was that at 15 minutes, the global agencies estimated magnitude to be about 8.1, and that wasn't really upgraded until about an hour and a half after origin time. And the real, final magnitude we're still debating about today, but wasn't really known for a few days. Now, an hour and a half of time for knowing a reasonable magnitude for the earthquake looks like this. This is where the tsunami was at an hour and a half before, by the time the magnitude was more or less correctly determined. It's already made landfall in Sumatra, it's already made landfall in Thailand, and it's about to make landfall in Sri Lanka. These are the 3 hardest hit countries. So this is not fast enough for what they needed. And it was then that the focus really shifted from talking about this sort of basin scale regional warning to talking about local warning, warning for the people right next to the earthquake. That's when that started. And I think the first paper to come out that really pushed this and suggested this was this paper by Jeff Blewett and Cornet and Bill Hammond and others at UNR with Seth Stein and Emil that looked at the 30-second GPS data that was available around the region at the time and said, hey, if only we had looked at the static offsets, we would have figured out that this was a very, very big event. So that was in 2006, a little over a year after the earthquake, and then shortly after that, a very nice paper by the GFZ group in Potsdam said we can go a step further. We can use these rapid magnitudes to initiate tsunami propagation models and perhaps issue local warnings that have not just a magnitude attached to them, but a forecast of tsunami heights. Meanwhile, the seismologists actually were also working. It wasn't just the geodesists. And I think it's safe to say that this W phase moment tensor inversion was a revolution in tsunami warning. This is the product that to this day dominates tsunami warning. W phase is simply this long period phase arriving in between the P and S waves that doesn't saturate and gives you the focal mechanism of the earthquake. So much so that in 2011, during the next magnitude 9 event in Japan, the Tohoku Oki earthquake that we just heard about a little bit in the previous talk and that you're all probably pretty familiar with, in this nice timeline put together by Gavin Hayes that shows when the NEIC produced all these data products that they're now quite famous for, it was the first time that they had a W phase solution for one of these gigantic earthquakes, and it happened at about 19 to 20 minutes after the start of the earthquake. So this was much, much better than what happened during the Sumatra earthquake. But 20 minutes is still a little bit too long, and unfortunately, the local tsunami warning system in Japan was not relying on these kinds of broadband measurements. So what ended up happening in Japan was that this is the first warning, tsunami warning, that went out 3 minutes after the start of the earthquake, when in reality, this is what the warning should have been like. This is when all the data were in, this is what the forecast actually had been. And 20 minutes in this fascinating, somewhat morbid paper, but that is very important, that number 20 minutes is important. They found when they surveyed why people survived, 20,000 people died in the Tohoku Oki tsunami. When they looked at why people survived, obviously it's complicated. There are many, many variables, but the conclusion that emerges from this paper in Earthquake Spectra is that when you start to move is one of the most important variables, if not the most important variables. You cannot shelter in place most of the time for a big tsunami. You simply have to get to higher ground, and for that you have to move as quickly as possible. So minutes matter. Every single minute counts, and that's why GPS becomes very relevant for the tsunami warning centers. Now, meanwhile, Brendan, while he was a young PhD student, figured out that if we started looking at these real-time GPS time series, he was the first one to notice that when you look at just the simple peak, the peak displacement of a time series, like here, there's a black GPS station. If you look at that peak value, when you plot it as a function of distance, you see some nice scaling. Back when we first did this, we had very few data, so few data points that we even put these magnitude 5 earthquakes that we managed to catch in Southern California because we really didn't have very much to go on. But what Brendan found is that Tohoku's up here, Takachioki's down here, this magnitude 7 in Mexico is there, and there seemed to be a nice scaling. A few years later, after collecting 7 more earthquakes, now we had 10, we continued to see that same pattern, that this peak ground displacement does not saturate. There's no indication that it will ever saturate as the earthquakes grow in magnitude or as you get close to the fault. We don't expect that it ever will. So we set about, and this is what the data set looks like now. So we now actually have, as we continue to scrounge high-rate data, we have about 33 events that Dara Goldberg and Christine Rule and others have been working on and processed that show the same pattern. But what's important is that we looked at how do we put that to work quickly for determining magnitudes. And we looked at these 10 events and we came up with a simple algorithm that takes that peak ground displacement and tries to figure out the magnitude of the earthquake as quickly as possible. And this is what it looks like. The take home is this, the colors don't matter here, but for Tohoku, by about 120 seconds, you know that it's a magnitude 9. Here's that magnitude calculation compared to the dashed line. For the Malay earthquake in 8.8, it's actually even faster. By about 60 seconds, you know the final magnitude. Incidentally, these tanned regions are the source time functions of the event, so very often you actually get a correct magnitude before the event finishes rupturing, in agreement with what Dara Goldberg showed yesterday. So we did this for many events and showed that it seems to work, and this and the fact that the data processing also has gotten a lot better. People at Scripps, at CWU, at JPL, really the precise point positioning in real time is also there so that we can routinely make record sections like this from the Tohoku-Oki earthquake. We come to expect that that's available in real time for every large earthquake. So those two things are really what gets our foot in the door with the Tsunami Warning Center. They say, fine, okay, tell us more. And that's what happened at this meeting. You'll see some familiar faces up there. That's Tim Melbourne, Tony Song, who's in the audience. This is the back of Brendan's head, and Zhen Liu at JPL. I think that's you, Dara, and this is Paul Whitmore and Stu Weinstein from PTWC and NTWC explaining to us what they wanted from GPS. So that was an incredibly, I thought, instructive meeting. And what we learned is that, or this is what they told us. They wanted, first of all, redundant sources of measurements. They wanted the positions for global stations to arrive from more than one path. So what that meant is that CWU, Scripps, and JPL would all provide solutions. And they wanted global coverage because PTWC and NTWC have a mandate that spans beyond the US. And they wanted something that speaks what the TWC speak, which is this protocol called Earthworm, which is for seismic acquisition and processing. It's a very particular framework, very much used by USGS and other seismological institutions. So what was built for them, mostly by Scripps, CW, and JPL in terms of data, was this complicated looking flowchart. Basically what this does is it takes this trial set of stations from all over the world, produces positions, and then Scripps sees CW and JPL's positions, CW sees Scripps and JPL positions, and JPL sees everyone else's positions. They're merged with a Kalman filter, and they're shipped off to both tsunami warning centers, and what they receive are 3 streams of positions for each one of these stations so that they can use for whatever modules. And the modules that, and this is what the data looks like. This is one station, Briones in Northern California. The CWU solutions, JPL and Scripps solutions, very similar. There's differences, of course. They each use their own positioning system, but they're very similar. They're merged and then shipped off to the warning centers. And then a bunch of modeling modules were built for the warning centers, not just this peak ground displacement magnitude, but also CMT solutions that use the static offsets and slip inversions that use the static offsets. And it more or less looks like this Franken monster, where that's the way the data is moved around and how different modules kick in when different things happen. What's important is that this has been a very deliberate, sort of almost sluggishly slow work, because these guys work in real time, so anytime something is hooked up to their system, they need to know it's bomb-proof and it works. And so we started with the data, shipping off the data, and we're now working on the models with PGD and the static offsets and the CMT solutions. And I'm very happy to say that PGD magnitude is now today operational at the National Tsunami Warning Center. And what that means, I think, is that when the next magnitude 9 earthquake goes off in Cascadia, using the current GPS infrastructure available in the Pacific Northwest, there's nobody from NTWC here to correct me, but when that happens, they would actually see the data, PGD would kick off, and they would have a PGD magnitude that hopefully would be close to M9 in 2 to 3 minutes after the start of the earthquake. So I think that is there today. It only took us 12 short years from that Blewett et al. Paper. Now, this is my favorite plot in this talk. This shows real-time replays of real collected historical data at NTWC. These are 10 events that are replayed through this entire flowchart in real time using this thing called Tank Player. Anyway, they're injected in real time into the system, and these are the PGD magnitudes that come out of that system compared to their real magnitudes. So for example, for Tohoku-Oki, it was an actual 9.1. What comes out of the system is 9.0 or 8.9. That works great. Some of them are really wrong. Here's the Iquique earthquake. For some reason, we get a magnitude of 6.5 compared to the 8.1 magnitude. I don't care. This is now running in real time, and these are errors that we can fix. This is not that there's anything fundamentally wrong with the PGD design. It's just there are bugs in the real-time implementation of PGD, but this is stuff that we can fix and that we can work on. So I'm very happy that this plot exists, because it means that this thing that has been painstakingly built over the last 2 years is actually there and running, and we're working on it. Now, the other thing that is becoming more and more important for these guys and for us as well is to not just inject historical data, but to also inject scenarios, especially for Cascadia, where we don't have any and will not have any historical data in the near future. So we're also working on building a whole suite. Right now we have about 1,300 of them, magnitude 8 to magnitude 9.2-ish Cascadia scenarios, and pushing them through the system. Here's one of those reported in Christine's paper last year. This is a magnitude 8.7 earthquake, and what you're seeing here is the GPS unfolding like a Swiss Army knife. Those are the 1 Hertz position, simulated 1 Hertz positions. Here's that slip pattern for Cascadia, and here's the rupture front propagating outwards. In this case, we also simulated strong motion data. Those are the squares, but those are not important for what we're doing with the TWCs. That was for a shake alert for another project. But what you see here is that the real magnitude of the event is this dashed line, and the real-time GPS code, the real-time seismic code saturates at about magnitude 8.1, which jives with what we've seen in other events. But the real-time GPS magnitude continues to grow, and by about 100 seconds, we hit 8.7 on the nose, and then it overshoots by maybe 0.1 magnitude units. But we're interested in doing as many of these to understand how well NTWC would be able to respond for a Cascadia tsunami. And as I said, we've made tons of them. So these are the 1,300 events, and this is the scenario magnitude down here, and this is the rapid magnitude up here, and the one-to-one line shows a good agreement. So we're mostly between the plus and minus 0.3 magnitude units for these events. There's some outliers. I mean, the system is not perfect, and earthquakes, and in these simulations, the earthquakes are different enough and complicated enough that sometimes we run into problems. But this is the kind of stuff that we're interested in. Why do we run into problems? Can we fix it? Should we fix it? So this is what we're doing now, and we're asking the question, how well do we model the earthquakes and the tsunamis? But really, the goal for PTWC and NTWC is to do this not just in Cascadia, but to go global. And this is a snapshot I took from the Nevada Geodetic Lab's webpage. This is every station that they're pulling in and processing all over the world. Evidently, many of these are not continuous, and most of them are not real time. But what this shows is that we should be able one day, perhaps in the not so distant future, to provide the TWCs with data from Chile, from Ecuador and Peru, from Costa Rica and Mexico, from Alaska, of course, from Japan, New Zealand, Indonesia, and have them do the job that they're already doing, but with the GPS data as that fourth tool. So I'll finish with this. Real-time GPS is somewhat operational at NTWC, and I think it's safe to say it's catching up at PTWC as well. MPGD is running at NTWC, and CMT and slip models from the GPS data are being worked on actively as well. Again, this is just another tool for the TWCs to use, because remember, the response is still hands-on, so there will still be a pop-up that says MPGD for this event, that the alarm just went off in the other room. MPGD is 8.3. They will look at their other data products and make decisions. That's the way they work now. And for future research, as we heard yesterday during dinner, one of the important things is, how do we identify shallow slip? That's still very tricky. With static data onshore, it's going to continue to be very difficult. So one thing to perhaps continue to think about is that when we incorporate time-varying data into the inversions, this is an example from the Iapel earthquake 3 years ago now, you can actually image slip to the trench if you have a code that can invert the high rate and maybe even the strong motion data. So that might be possible. And the other thing is, if we can generate thousands, millions of these synthetic scenarios, do we believe that those simulations are good enough that we can use them to train machine learning models that recognize patterns, and then we can maybe circumvent the whole business of inversion altogether? But that's up for debate. And finally, the last chunk of future research, I think, is to remove that hands-on component that is still going on at the tsunami warning centers, to run propagation models quickly as the GPS data produces a solution. But we still have to prove and show to the TWCs that those quick models are actually reliable, and ask them if they think they're useful. Here's an example from the Malay Earthquake here at the top. What this black curve shows is the tsunami amplitude at the coastline for that Malay Earthquake as best as we can reconstruct it. This is our best guess of what actually happened during the Malay Earthquake at the coastline. This is not run-up. This is exactly at the coastline. And the colors are the level of warning based on some scale that each county, they're called regions in Chile, that each county would have received during that earthquake. Here on the right is the GPS inundation model as it would have been available in about 3 minutes after the start of the earthquake. The black line shows the same thing. Evidently there are differences, but the peak values are more or less the same. And the warnings for every region are also similar, even if they're not the same. So in the case of the Malay earthquake, this worked out great, but in the Illapel earthquake in 2015, here's the real amplitude of the tsunami along the coastline, and here's that rapid GPS inundation amplitude along the coastline. We missed it because it had so much shallow slip here and the network geometry was not so favorable. We missed this broad peak. Is that a problem? Are the tsunami warning centers still going to use this? Do they still find this useful? And is this a systematic issue that happens with the scenarios and other historical events? So that's the final thing that we should be working on in the near future. And to finish, I focused here exclusively on tsunami early warning because I think it's where the immediate benefit of GPS is the most obvious, but real-time GPS will also be a big player in Shake Alert. This is the West Coast-wide earthquake early warning system that will be live this year. There will be limited public release of that system. It will begin issuing alerts to the public. In its first version, it will only use seismic data and it will only have point source algorithms. But we expect that real-time GPS will be a main component of Shake Alert version 2 and going forward, especially to identify things like fault finiteness. This is also from Christine's paper. This is a simulation of ground motion for one of these scenario events, fake quakes we call them. This is what the ground motions look like for that fake quake. This is the seismic estimate of ground shaking at 16 seconds with just the point source. And once we have some guess of fault finiteness from GPS, this is what the ground shaking estimate looks like. So GPS really does have a big role to play there as well, but it will be in the second version of Shake Alert. And I'll finish there. Thank you.
Perfect timing. So we have a chance for some questions for Diego. Yeah, please come up to the mic.
There's no microphone.
Oh, sorry. Yeah, I don't know. I think they're recording, but keep one back there.
Hi, so that's a great example of research to operations, and I was kind of curious about going the other way. If PTWC had a need operations, how do they push that back to research, and would that be timely for them?
Yeah, that's a great question, and this, my favorite plot, that wasn't made by me. That was made by one of the staff scientists at PTWC, and it's a great example of what you described, where they take our idea, they run it, and Ken has also tried to fix this and come up with reasons why this is happening. He's also very involved in running the scenarios. So there is a lot of backwards and forwards with some of the PTWC and NTWC scientists. I think, to me, one of the big remaining challenges in this kind of work is that it takes a long time for us to iterate with each other between a discovery that is made in science and push it out to the warning centers and for them to run it and tell us what they think and send it back. 12 years from Jeff's paper to this. And I think we have to find some way, some framework to speed that iterative process up because people are working on a lot of exciting stuff. And I don't know exactly how we do this, but a big challenge is that they work in Earthworm, I work in Python, someone else works in MATLAB, he works in Fortran, and when we have to translate one to the other, it's a big pain in the butt. And we need to speak some common language or work on some common framework that allows us to do this. But the PTWC scientists and the NTWC scientists are very involved, and they continually kick stuff back to us and say, hey, what about this? So they're very engaged.
And then that brings up the idea of validation on that point.
Yeah, so that's what this is for, the historical earthquakes, that these are just the 10 that we had originally. We have 33 now. We're in a concerted way running every module. In my vision, another thing gets added to this flowchart where maybe every day one of these gets run and spun up, and we see that the output comes out and we validate that nothing has been broken and that we still get the output that we expect. So the historical events are very, very important for that, and also the scenarios that we're building. But it's still unclear how much weight should be placed on the scenarios. If the scenario earthquakes don't behave in a certain way, would we be comfortable in making changes to the code based on the scenarios? So that's a kind of debate that is still ongoing. But for now, these historical events are the real validation of what's going on.
Thank you.
Yeah.
Noelle?
Yeah. Thanks, Diego. That was a really great talk. I wonder what you think about the fact that, of course, the GPS is going to be least sensitive to really shallow slip out near trenches, which is, of course, the most important slip for tsunami early warning. You touched on that briefly. I wonder if that's maybe part of the problem with the Iquique earthquake here as well. So I guess I'm just wondering, can that problem be mitigated by integrating the GPS with seismic or other observations to fix this, lack of resolution of the very most important slip for tsunami early warning?
So surprisingly, I asked them recently with the Kodiak earthquake, that strike slip earthquake offshore Alaska, if they had a moment tensor in 3 minutes from the GPS. I asked them would that have changed, because the warning went out wide when that earthquake happened. I asked them if it would have changed their response, and they said probably not, because they just want to play it safe, and if a 7.8 happens at shallow depth close to the trench, they're just going to go with it. It doesn't matter what the mechanism is. So part of the challenge, again, is to get them to be comfortable with using these products to inform propagation models and run them and issue warnings based on them. Specifically for the issue of resolution, absolutely. If we can jointly, as we saw last night, if we can do that in real time, they will do it as long as we show them with 30 events and 50 scenarios that it works and that we help them build a real-time code to do that. Absolutely, yeah. It's just a lot of work to go through that iterative process.